Talk of the day, Alicia Dickenstein from University of Buenos Aires. We'll talk about real and sparse intersections.
Thank you very much. I'm happy to be here. So this lecture will be different from the other ones. So I still work in theoretical aspects of residues and toric varieties and other stuff. But I've also been working with applications mainly to biochemical reaction networks. So I will not speak about the applications, but I will speak about questions that are important for the application. So I will just explain what this talk about. I'll give some easy examples. So it's an elementary talk. And then I will show you some tools using the generations and some bounds for local multiplicity and a little bit of the mostly unknown multivariate Descartes rule, and then we will end. Okay, and as I said, I will not talk about applications, but I will describe the mathematical questions that arise and that are mostly unsolved over the real numbers, okay? Okay, so you don't need to read this. I just say I'm not going to speak about the applications, but about the questions. Okay, so what you see in red is a smooth quantec. So it's a graph of a polynomial of degree 5, okay? And maybe you see, so if you, over the complex numbers, if you intersect it with a line, a generic line, you will get 5 complex points of intersection, okay? But now, if you concentrate on the number of reals intersection here, this yellow curve will have 1, 2, 3, 4, 5 points, but all the other lines have less points. Here, we will only have 1 here, and 1 there, and here we have 3 again. So there is no generic behavior if you try to count the number of real roots. Okay, the space is split into different numbers of real intersections. And so this is the first very easy observation. And then this is, for instance, if you have a two polynomials, in 2 variables, you can make them homogeneous if you wish. But 2 polynomials in 2 variables, I will mainly speak about affine setting. So what happens with applications, something that was in the first slide, is in general, depending on the problem, you get some monomial, some structure, and you get many parameters. You naturally get families, and the monomials that occur are usually fixed. These are not all monomials of degree up to D or whatever. Okay? So in general, you could have 2 polynomials with these monomials. This is y to the d, x to the d. This is a constant, and x times y. Of the complex numbers, if I take generic a's and b's, we'll have d squared isolated, the Bezout number of complex solutions. But over the real numbers, we prove that you cannot have more than 2. If the coefficients are real, and if you look for positive real solutions, you cannot have more than 2 positive real solutions. And this is because, on one side, you have only 4 monomials. On the other side, the combinatorics of these exponents, that one exponent is inside the convex hull of the other one, restricts the number of positive roots. Okay, so we consider the configuration which is given by the columns of this matrix. In fact, this is called the Cayley matrix. I have one configuration which is given by these 3 points in the plane, 6, 0, 0, 3, 0, 1, and this other one, 0, 6, 3, 0, 1, 0. And this is the associated Cayley matrix. This corresponds to getting like T1 times the first equation plus T1 times this second equation. This is a trick that goes back to Cayley, transforming a complete intersection into hypersurface. Okay? So this would be the monomials, the exponents of the monomials in such linear combinations. So if we take 2 polynomials with this, the first one with these exponents, t to the 6, s to the cube, s to the first, and the second one with these exponents, and we have varying coefficients. We have a family with 6 parameters, y1 up to y6, okay? And then there's what's called the mixed sparse discriminant. is a polynomial that vanishes. It's in fact an irreducible polynomial that vanishes whenever there exists a common zero, which is not simple. I mean, when there is a point of intersection where the Jacobian also vanishes, then the discriminant vanishes. Okay? If you are outside this means that all points of intersections are simple. You could have all points of intersection and still vanishing because it's the closure of points where there is, some small issue with the closure. So you take the points in the torus where the intersection is not simple and you take the closure. Okay, so this is the discriminant. Why are we interested in this? Also, let me tell you, the discriminant can be computed. So if you heard of Rebner basis or whatever, or use Macaulay, maybe you don't think what you're using, it's an elimination process, okay? And then you need to find a condition on the coefficients, knowing that there is an x, which is a zero of the h and the Jacobian. And then in this case, I'm not considering the whole discriminant, but I am fixing some of the coefficients. Instead of y1 up to y6, my coefficients are 1a minus 1, 1b minus 1. So here, let me look. So I'm going to put here 1a minus 1, 1b minus 1 as coefficients, okay? And this discriminant equals this. This is the beginning of the polynomial. So we had polynomials with really small degrees. It's tiny, three trinomials. And the discriminant is a polynomial of degree 90 with 58 monomials and huge integer coefficients. So you see that it's hard to deal with this discriminant, even if this very simple case. So in fact, it was known by a paper. I didn't put the year. I forgot to. I think it's 02 or 3 or 5 at the beginning of this century. They proved, Lee, Rojas, and Juan proved that if you have two trinomials that the ones that I showed you, the number of simple positive real roots is at most 5. And there was a first example given by Bertrand Haas of degree 108. But using the mixed discriminant, we found a smaller example with degree 5. I will show it to you. And we found the point, this A equals B equals 44 divided by 31, where there are 5 real roots. But the area of the set of points for which there are 5 positive real roots is tiny. It's smaller than 5.7 times 10 to the minus 7. This means that if you do any sampling, you will miss them, this thing. Let me show you. So that just the motto is that it is hard to find real sparse polynomial system with many real solutions. So how could we do this? Well, the story is that you have the discriminant. What happens is if the number of real roots is going to change, you need to cross the discriminant. The only way is there are 2 complex roots that meet, okay? In order to change, I'll say it again, in order to change the number of real roots, you need to cross the discriminant. Because the only way is that if there are 2 complex roots that come together, and then they become real, or they disappear. Maybe on one side they disappear, and the other side they produce 2 real roots. And then if one is able to draw discriminant equal to 0, we look at the chambers of the complement, the connected components of the complement. Okay? In general, the connected components of the complement, the number of real roots is going to be the same. This is a particular case in which these 2 polynomials cannot intersect at the point on the axis, but only at the origin, the only point where the intersection could happen. And then it also happens that if the number of real roots is the same, the sign of the roots does not change. In particular, the number of positive roots does not change. So these chambers really represent, in fact, in the complement, there is a finite number of chambers. So in principle, somewhat easy. I pick a point in one of these finite number of chambers. For these points, I compute how many positive roots I have, and then this is the answer for all the parameters in this chamber. But if you try to do an implicit plot, I show you the polynomial, it's going to be horrible. You're not going to see anything. But instead, the discriminant is a rational variety, and it's easy to parameterize it. In fact, it's just there is a translate by the torus action given by the columns of this matrix of a linear space, of the kernel of the matrix A. Okay? So it's easy to parameterize the discriminant. So using the parameterization, I say we, but this was made by 2 undergraduates at that time who really worked hard to do this picture. So, and they had to work in logarithmic scale because at some moment they scale up to a factor of 1700s. So the first plot of the discriminant is this one. And then the second plot, we are just zooming here, is this one. And there's kind of like fly here, right? You see there's something here. And then you go on, this is 1700 times. And here you find this red region, and in this red region you find 5 positive roots. Okay? And so this is a picture which is not to scale, which is the following. So these are supposed to be the chambers in the complement of this discriminant. And this is the number of positive, depending on first negative, second positive, this depends on the sign. This is the number of real roots depending on the sign of the coordinates. And you see that the maximum number of real roots is 3 plus 6, 9. It's here, in this part here. In general, what happens is that there are some chambers that go to infinity in some direction. And in general, the maximum number of real roots will be in this chamber. But here, the maximum number of positive roots in this small area, but here it's big, but this is not to scale. It's here, it's 5, and you see that when there is the maximal number of real roots, it is not the same region when there is the maximal number of real roots. And what happens, so this is very tiny, and this is very close to these intersection points here. So it's very close to points which are not only the discriminant, but are in the singular locus of the discriminant. And they are very singular. So we have a tiny region, and it's very close to very singular points of the discriminant. Okay. So this is based on an article where we use this idea. So I will read this afterwards. Let me show you the picture. This picture is supposed to tell you what is a regular subdivision. So I have, you can think that you have polygons or polytopes, but you really have the support. So have polynomials, and the exponents in my polynomials are these black dots downstairs. Okay, I have a polynomial in 2 variables, and these black dots represent the exponents in the polynomial. Okay? Then we take any height function h. It could be down positive or negative, but it's easier to see it there, and it produces the same effect. So we take any generic heights, or not generic, any height h, and then we take the convex hull of the lifted points and take the lower hull, those points with positive last coordinate. The normal has positive last coordinate, and we project. We project the domain of linearity of this lower convex hull. And this produces what's called a regular subdivision of what we have below, of the convex hull of the points, if you wish. For instance, this point here, the height is higher. This point will not occur in the subdivision. Not all points, for instance, if one way is lifting everything to the same value, h equal to 1, and then when you project, you will not subdivide anything. But this is it's not just, and if h is general, you will get a triangulation, but it's not any triangulation. It's a regular or coherent, which means that comes from a lifting. And I will explain you why this is important. And so using this idea, this goes back to Vito and many other people who work with this. So there's a nice paper by Bian, Santos, and Spanlauer. And they use this to get a lower bound on the number of positive roots, and they get some interesting combinatorial obstructions. This is a very nice paper that appeared in the SIAM Journal of Applied Algebra and Geometry. And this was also used long ago by Bernstein to study real roots of complete intersections with sparse inputs. Sparse means that you fix the monomials that are going to be present in your polynomials. Okay? It could be all the monomials of degree d, but sparse means in general you have less than that, and that's why the name is sparse. Okay, so let me give you an example. So I have this system of polynomials here. If I have a system of polynomials, I can think that I have two informations. One is which are the exponents, which are 0, 0, 2, 0, 0, 1, 2, 1, 1, 2, and also have 1, 3 here. So this is the set of exponents. And then the matrix of coefficients. So I have this matrix C, 1, minus 2, 1, 1, minus 1, etc. Okay? And here I have a 0 because there is no y term there. So I have the coefficients, and I have the exponents. So this means this equal to 0 means that the matrix of coefficients times the vector of monomials with this exponent is equal to 0. So for instance, you see that there is an obstruction to find a positive solution. Is this matrix need to have a positive vector in the kernel, for instance. Okay? This is easy to check. I will go back. And how do you check this? The way of checking this is go back to Kramer's rule, and it's in commutative algebra. I don't remember the name, but you will see. So the condition under which you can find a positive vector in the kernel is the following. So you take your matrix. I will go to the next slide. Before this, let me tell you. So how many roots do you expect? So this polynomial has degree 3. This has degree 4. So the Bezout bound is 12. You expect to have 12 roots. But in fact, it is sparse. Some monomials are not present. So we have a better bound, which is the BKK bound. So the number of isolated solutions is at most the volume of the convex hull of the exponents. So these are the exponents 0, 0, 2, 0, 1, 3, etc. And this volume is the integer volume. In this case, it's just 2 times, or 2 factorial times the Euclidean volume. So at most, we can have 8 solutions in the torus with complex solutions with both coordinates being non-zero. Exactly. If we remove this point, the number won't change. And if you add more points, it won't change either. Okay, I will skip this for a moment. I will go. So I had this system, and this was the support. And here, what you see is one possible regular triangulation. You have to believe me that this is a triangulation, it's a regular triangulation. And then I have colored with violet, I don't know which color is this one, these 4 simplices, and not this one. This is because these 4 simplices are decorated by the coefficient matrix. So I have my exponent. This picture comes from the coefficients, from the exponents. And I have a second information, which is the coefficient matrix. So what does it mean that this simplex is decorated by the matrix? So I have the matrix of coefficients. I have all this matrix, but I only look at the coefficient that correspond to these 3 monomials, which is this first part. Okay? If I do this, if I have a simplex, I have n plus 1 points in dimension n. Here I have 3 points in dimension 2. So we are going to get a matrix which is of size 2 times 3, so k times k plus 1. Okay? So when do you have a positive vector in the kernel? There is a generic solution. When the kernel has dimension 1, there is a generic symbolic solution. This really goes to Kramer's rule. So, what you need to have is that you take away the first column, you compute the determinant, you get a 1, minus 1. Then you take away the second one, and then the third one. When you start taking away columns and computing determinants, then you need to have alternating signs. If you want to have a positive vector in the kernel, what you should have is that if you start taking away each of the columns and computing the determinant of what's left, then the sign should be alternated. Because then the vector in the kernel is minus 1 to these determinants, minus 1 to the ith determinant. So this means, in fact, that In this case, this simplex delta 1 is decorated because the minors are -1, +2, and whatever you can do this, plus, minus, plus. And it's, in fact, what we are going to have in general is not a linear system, but the fact that over the real numbers, the nth root of the real numbers is bijection. Taking roots is bijective from the real to the real, so you don't care about the exponents. And so this means in this case that one can check that these 4 are decorated and this is not. And this, in fact, it is easy to see that it is impossible to decorate all of them. You need some signs of the minors, and it gets incompatible if you have an odd number and it closes. And then what happens is, so we had 4 decorated simplices. In this case, with the coefficient that I gave to you, there are only 2 positive solutions. But the theorem what says is, okay, maybe your polynomials don't have 4 positive roots, but there is a way of degenerate the coefficients in order to get 4 roots. How you degenerate the coefficient? This is a standard toric degeneration. So the standard way is you pick any height which gives this subdivision. In this case, this height will do 1, 0, 0, 0, 1, 3. And then the theorem says, okay, then in the first monomial, you multiply by t to the h1, second by t to the h2, all the way. Okay? And the theorem says, if t is sufficiently small, then this polynomial is going to have 4 positive roots. And in fact, it's easy to understand what is happening here. And you can compute here, in this case, that t1/12, it's enough. The idea is, if you just concentrate in one simplex, imagine that you put all the other coefficients equal to 0. Then you just get this simplex. So the idea is that if I just start moving a little bit the other coefficient, I will still have these 4 simplices if I can use the implicit function theorem. I put all of them to 0, I concentrate in this simplex, and then one expects that there is an open set in which you could extend this solution. But then if you have 4 simplices like I had, you need to extend this, and this. You have 4 open sets. And what is the magic that tells you that there is an intersection point in these 4 open sets is the height function. The height function ensures that there will be a non-empty intersection of the open sets in the coefficient space where you can extend each of the roots. Okay, and then in this case, there is a symbolic command, which is, for instance, implemented in Singular. It's also implemented with a different name in Maple, that go back to beautiful work of Hermite. So there is a symbolic way, if you have an ideal which has a dimension 0, finite number of complex roots, then there is a way of computing how many positive roots or how many roots in some semi-algebraic set. And this uses a story of signatures that goes back to Hermite, which is very beautiful. But you need to have specific coefficients, because otherwise there are too many branches. If you want to do it parametrically, it's a mess. You cannot do it. But with fixed coefficients, you can compute it. So in this case, you get indeed 4 real solutions in this example. 1 second. But in general, you get more than 4. So this 4 is the number of decorated simplices is a lower bound. Yes?
Sorry. When you showed us the picture of the complex pool of the points,
yes.
You showed us that the volume was 8, and that bounded the number of solutions by above, right?
I told you that the number of solutions in the torus is at most 8. So in particular, the number of positive solutions is at most 8.
Yes. So, but then with this subdivision and decoration of the matrix, you told us that you can move the system so it has
at least 4.
But I'm wondering if this also gives you information, like final information of at most how many solutions.
At most? No, we don't know. We don't have a sharp lower bounds, we don't have sharp upper bounds. This is completely open, almost. So this is, I want to show you this because it looks at theorem in analysis, but it appeared in the Journal of Algebra. So this is, so forget about don't read the letter. So our idea is we didn't want to have a curve. So the standard thing is to take t to the h. So you have a curve, you deform your coefficients following the curve, t to the h1, t to the multiply. But we wanted to have an open set in the space of coefficients where we had 4 positive solutions. How do you get an open set? Okay, so instead of picking one height that produces this subdivision, you take the cone of all heights that have these simplices in your subdivision, these decorated simplices in your subdivision. You take the cone of all possible ages. And with this cone is a polyhedral cone. It's an open cone given by some linear inequalities, and somehow in not so obvious way, but this, for instance, this could be 3 times h1 plus h2 plus h7 positive. You take the coefficient of this linear form, and you put it as exponents in a monomial. So if you pick gamma, so that gamma raised to this same linear thing is sufficiently small, then you can move gamma there and still have 4 positive solutions. It's hard to express this open set, but you get an open set. But the idea is that instead of taking one edge, you take all possible heights. Okay, but then if you are working in practice, so even if deciding if a bunch of simplices is part of a regular subdivision, this is algorithmic, this is too difficult. And we were working with any number of variables, big number of variables. So there's a simple idea, say, okay, if you have 2 simplices that share a facet is a face of codimension 1, if they share a facet, even if the union is not convex, then they are always part of a same regular subdivision. Then what we try to do is, even if there were many variables, to find just 2 simplices sharing a facet so that we could decorate both. But this was interesting. We are writing an article now with Rick Richter, was a former student of Carolina, and he made an implementation in Maple. And the implementation was correct, but we didn't get one possible case that occurred in the thesis of a student of mine. So at the beginning, I said, oh my God, the thesis is wrong, and then there's a paper published, and we use this for another paper. What is happening? You know, I was so worried. This happened 10 days ago. Why? What is happening? And then I realized that it is very hard, because I tell you it's easy in theory to say that something is decorated, but our coefficients are in fact rational functions, some other things, and deciding that if the minors are positive or not is the time where some rational functions have some signs, if it is possible to have a bunch of rational functions with signs that produce a non-empty set. This is a non-trivial thing. You need to decide if a semi-algebraic set is empty or not. And this is very complex in the sense of complexity. And the problem is that there is no good implementation of real algebraic geometry, in fact, of deciding semi-algebraic set. There are some implementations, and Rick proposed to use a command that used to optimize something over the set, so optimize the function 1. And we got no answer because apparently the set was empty, but the set was not empty. The problem is that it is very hard to decide whether it is empty or not. Then when they discovered that the problem is that the software couldn't decide if it was empty or not, we were able to retrieve those subdivisions that my students had found. But anyway, so I say when one does not try to compute, I think there are things that seem kind of easy mathematically, but in practice they are very complicated. Right? Okay, but what I was telling that in general, we get only a lower bound. It's not sharp in general. And there are other results based on degree theory to get lower bounds, but this result is just the sum of the signs of the Jacobian. At most, you can get a bound of 1. And at most, you can use this result in degree theory to assert that there is at least one solution. But it's hard to get more than one from these bounds. Okay, so there's a really, really, really open question, how to get sharp lower bounds on the number of positive solutions sparse polynomial systems. The only one that I'm aware of are the degree story and this polyhedral subdivision. Okay, now let me change subject. So we are going to talk about bounds for local multiplicity. So what's the local multiplicity? So I have a point, which is an isolated intersection. In my case, we are in dimension n. It will be the isolated intersection of n hypersurfaces. So in this case, the local multiplicity is just the dimension of the local quotient. Okay? We want to understand which is the possible dimension of the local quotient if I have n hypersurfaces with fixed support. Okay? So the setting is I have my exponents, and what is going to come into the picture is the number of monomials, not just the degree, not even the convex hull, but the number of monomials. So we will assume that the number of monomials is m plus n plus 1. And we are going to call n is the dimension, and m is going to be the codimension. It's the dimension of the space of affine relations among my exponents. Because, okay, if you are looking for solution in the torus or positive solutions, you can multiply any polynomial by a monomial, and this won't change the positive or solutions with non-zero coordinates. You can move them. So in fact, what you're interested in is in the affine relations among the points in your exponents, not the linear relations, because you can move them freely. And also, this is why you get the Cayley matrix showing up. So we are going to take polynomials fi with these exponents, n of them in n variables. Okay? And this could be in z, this could be Laurent polynomial exponents, could be in principle negative. But as I said, you can always multiply by a monomial and put all of them positive or non-negative and get the same number of positive solutions. But here, we are not dealing in principle with positive solutions. I'm dealing with solutions in the torus. Okay? So in the torus, it's just c star to the n, non-zero complex numbers. And the question is if it's possible to bound the maximal local intersection multiplicity at one point in the torus if you are dealing with monomials, which m plus n plus 1, polynomials with this number of monomials in n variables, okay? And of course, there is a global bound. We have the BKK bound that I told you before, which is the volume of A. This is how many positive solutions, solutions in the torus you can get in general. The multiplicity at one point cannot be bigger than that, so there is an obvious upper bound. But in fact, it is easy to see in one variable that the multiplicity depends on the number of monomials. So for instance, if I pick any d, I take the polynomial q as any non-zero number. Q could be equal to 1. Q, x minus q to the d. It has d plus 1 points in the support from 0 to d. They are the exponents. It has multiplicity d, but all the coefficients are non-zero. So just write x minus 1 to the d. The coefficients are 1 minus 1, or the combinatorial numbers with sign, but all coefficients are non-zero. As soon as you put a 0, assume that one of the monomials is not there, it is easy to see that you cannot have more than the number of monomials minus 1 as the multiplicity. And the proof is easy. So I take this f, and I take q, which is a root of multiplicity mu. This means that f vanishes, f prime vanishes up to the derivative mu minus 1. And then this means that this vector is a non-zero vector in the kernel of the van der Monde matrix associated to the coefficients. And this matrix, we know, has maximal rank, and if you need to have a non-zero vector in the kernel, you need this condition. Otherwise, you will not be able to find a non-zero vector in the kernel. So it is easy to see in one variable that the maximum multiplicity at one point is at most the number of monomials minus 1. And this is the number I'm calling m plus n in general. So this is the question again in terms of the dimension, the codimension node, and the volume. As I said, this is just the vector space dimension of the quotient. And so there is a previous result by Gabrielov on 95, and he proved that the intersection multiplicity of the point in the torus cannot exceed this number. It has 2 to this big number, etc. And what we got is a quite smaller bound, but with further hypotheses. Okay? So the story is the following. We wanted to use a combinatorial tool, which is the mixed covolume. So there is a combinatorial local version of the mixed volume on this BKK bound is Bernstein, Kushnirenko, Khovansky. I don't know which order is there, the 2 cases, but using these combinatorial tools. Okay, I'm going to skip the definition of non-degenerate. So I didn't end my sentence. So what we're trying to use is the covolume. To use the covolume as a measure of the multiplicity, I will explain a little bit what this is. We need to assume that the system is non-degenerate. I will not define non-degenerate for the moment. Let me not do this. I will try to explain a little bit because it's technical. It will take many lines. I don't want to do this. I will try to explain to you later what this means. But if I have if Q is a solution, and this story of covolume only can be done if the point is the origin. So we need to move our point to the origin. So in principle, in theory, it's very easy. You move your point to the origin. Instead of considering your original small f's, you define capital F, and you move them by Q, and now you have moved the point of intersection to the origin, except that we have lost sparsity. And in this computation, what is interesting is that the exponents and the coefficients start mixing up. Because if you take x plus q to the second power, you will have x squared plus 2qx plus q. And the 2 is, so the exponents will start occurring in the coefficients. We'll get polynomials which are no longer sparse, and where the coefficients have a mixture of exponents and coefficients. And then the theorem says that if we have a finite A with full dimensional convex hull, so this means that polynomials with exponents in A really depend on n variables and not on less variables, so you expect that the number of, you expect an isolated, a finite number of solutions. Then, this is a theorem says, okay, I'm trying to be non-technical, but maybe it's worse. So there is also to compute the multiplicity using mixed covolumes. You need that the system is convenient. I will explain this, and you need it to be non-degenerate. But here we prove that in general, if the maximum multiplicity can always be attained with integer coefficients. If you're looking for a maximum multiplicity, you can assume that you have integer coefficients. Okay, so what's a mixed covolume? So we take all convex polyhedra and we do the following. Given one point, we take the whole orthant. We take the whole orthant at each point, and you take the convex hull. And then you look at what's behind the lower faces. So if my input are these 3 monomials, 3, 0, 1, 1, 0, 3, this would be my delta. And then I look at all these polyhedra so that if I take the positive orthant and I put a positive orthant at each point, the complement is bounded. For this to happen, I need to be touching all the coordinate axes And this is convenient. Convenient is that I'm touching all the coordinate axes. Otherwise, I will get a region with infinite volume behind. And then the mixed covolume. So for this picture, the covolume would be just, I have 3 times 1. 3 times 1, the Euclidean area is 3/2, but the integer area is 3. In this case, I'm getting 6. And the Newton diagram is the union of these two faces that can be seen from the origin, of course, of this point too. There are 3 faces, this, and the 2 edges. And the mixed covolume is a unique symmetric multilinear function that when you take all the same polytope, you get essentially the volume of this area. So if you don't know anything about mixed volumes, maybe this is too quick, but there is a combinatorial way computing volumes of computing multiplicities. The theorem says if you have polynomials or power series, convergent or not convergent, that where you can define the multiplicity at the origin, then the system is convenient. If the system is convenient, if it touches all the edges, then the multiplicity at the origin is at least the mixed covolume. And it equals if it is non-degenerate at the origin. Non-degenerate at the origin means that if you have 2 polytopes and you have 2 faces, one is in the Newton diagram of one polynomial and the other one is in the Newton diagram of the other one, and they are parallel, then you can restrict your polynomials here. You will get homogeneous polynomials, but essentially in 2 variables, but essentially they depend on 1 variable. And you ask that these polynomials don't have any point of intersection in the torus. It's like not having roots at infinity in some sense. And then what we proved is under some hypothesis, we get a much smaller bound. Which is this one. But what happens is that being non-degenerate and convenient is not a generic property. It's generic once you have fixed the mixed volume, but otherwise it's not. And to prove this, we need to use Gale duality, and we got a very interesting duality. We start with a polynomial in n variables. You get a polynomial in m variables, the codimension many, where the exponents are the coefficients and the coefficients are the exponents. And it doesn't matter if you have complex coefficients as exponents, so x to the a. If a is a complex number, you can define x to the a is a holomorphic function, and you can expand it in power series, so you can still compute this. This is not a problem. Okay, so what we were trying to do, we were trying to find what we were trying to do, we were trying to find polynomials with high local multiplicity. And we proved that these polynomials, look, that the exponents here lie in the rational normal curve. The exponents are k, k squared, k to the n. These are the exponents, and these are the coefficients. And the idea is we proved that these polynomials have very high multiplicity. So how do we start thinking of them? Each of them is as singular as possible. The point we chose is the point 1, 1, 1, 1. So we chose each of them as singular as possible. But you cannot choose all of them as singular as possible. You need to start decreasing. It's easy to see, but the idea is if you want to have high multiplicity, you need to start with polynomials which already are very singular. And then we proved that the multiplicity is at least this number, which is nice, which is symmetric in n and m. Okay? And we conjectured that the multiplicity is this number, but we could only prove it for n equals 2. And let me tell you which was the difficulty for n equals 2. So we computed the Newton diagrams. So this is the Newton diagram for one of the polynomials, and this is the Newton diagram for the other one. So they have these two faces that are parallel, and we need to show that these restrictions, the polynomials there, did not have any common root. And we found, and a former student of mine found this over the internet, that we were dealing with Laguerre polynomials. These are well-known hypergeometric polynomials. And one, with our choice, one was the derivative of the other one. And it is known that these polynomials interlace their roots. That these particular hypergeometric polynomials, you have f and f prime, the roots are precisely interlaced. One is between the two roots of the other polynomial. And then if they are interlaced, they are not equal. But in general, it's hard to do this. Okay, so just let me go quickly. Also, don't read this, but we proved that if the codimension is 1, then the only way in which you can give this maximal number of points of multiplicity is if your points lie, if your exponents lie on the rational normal curve. Otherwise, it's not possible. This means that these points are vertices of what's called a cyclic polytope, and cyclic polytopes are very much known in combinatorics because they have several extremal properties. They have the maximal number of faces of any dimension, and they are very much well known in combinatorics. But the story is the following. So we don't know if which is indeed the highest multiplicity that one can get. We assume it is this, but we don't know. And we also would like to know for which configurations this is possible. So this is not known. But what we were really looking for, why did we land into this question? What we wanted to have is a system with many positive roots. So our idea is the following. I start with a system with very high multiplicity. So I start with a system with multiplicity 1,000. If I move a little bit, I will have 1,000 simple roots over the complex numbers. Just a small perturbation will give you simple roots. But how many of these roots are real? So our hope was that we would be able to get many real roots, many positive roots, just moving a little bit the coefficients. But this is, again, a hard problem and completely unsolved. Because somehow what you would need to do is to construct some kind of real Hilbert scheme and understand what happens, in which direction to move in a very singular point of this real Hilbert scheme to get in a real direction. Here I was saying, is it possible to perturb a singular system to get many real solutions? So how? And this is completely unknown. Because even if we look at some kind of real Hilbert space, which is a scheme which is not constructed, we need to understand what happens at the very singular point, not at there's no tangent space. There's no natural way of getting the deformation, at least to my knowledge, and I think that it is not known. I asked people who work with real algebraic geometry, and the answer is no. It is not known, nobody knows. One knows to move away, but not using implicit function theory. Away of that, one needs to move. And as I said, the problem is that we are going to be very close to a point which is a singular point of the discriminant. At this point, the multiplicity is high, so the coefficients lie in the discriminant, and we need to say we are here, and we need to say in which, so here, what happens if you move here, you get only one positive root, here 3 and here 5. So if you are here, there is only one way of moving in this tiny region in order to get 5. But how do you decide that there is a region, and in which direction? So the theory, to my understanding, is not done. It's completely open. So also this is maybe kind of anecdotic, but for me it's interesting. It happened to us that we have some results bounding the number of positive solutions, the global number of positive solutions, and the local number of the local intersection multiplicity over the complex numbers. And somehow we got the same bounds. Okay? So it's at least in the dimension 1, in the case of a circle, it's n+1. And our question is there any relation? Why is it that the same numbers seem to occur when we look for global number of positive solutions and local number or local multiplicity of a complex solution? And we try to argue some heuristic explanation using stable intersection in tropical geometry, but I don't know if this is true or not. So we really don't know if this is the case or not, but it is puzzling that they seem to be related in a way that we don't understand. So I have 10 minutes, right? Because I started a little bit late. Okay. So do you know the Descartes rule of science? Have you heard of this? It's beautiful, easy. In fact, Descartes did not prove it. He stated for a polynomial of degree 3, but it is very easy to prove using Rolle's theorem. What he says is the following. So if you have a polynomial with some exponents, with real coefficients, you would like to know how many positive roots you could have. And the theorem says you cannot have more than the variation of the signs of the ordered sequence of coefficients. So for instance, assume that this is your polynomial. So I forget about the zeros. The signs are plus, plus, minus, plus, plus. So I start, there is no sign variation. I go from plus to minus, there is 1. From minus to plus, there is 2. So this means that this polynomial has at most 2 positive solutions. And the parity has to be the same. So it has either 2 or 0. And this is complete. I put 111, but it could be 111 million. So it is completely independent of the degree. So the number of complex solutions is the degree. The number of positive solutions is at most the number of sign variations in the ordered sequence of coefficients. Okay? It's so simple. And it's great because when all the roots are real, for instance, if you have the characteristic polynomial of a symmetric matrix, this is exact. You get the exact number. Okay? It's not just the bound, it's the true number. If all roots are real, you get the true number. So it doesn't say anything about your polynomial. Okay? It's an assertion about the family of all polynomials with these signs in the coefficients. And it is sharp in the sense that it's always attained. Okay, and then in many variables, so what this says, as I said, is the first thing that it says is that the number of monomials bounds the number of positive roots. And in many variables, this was conjecture, and this was proved by Askol Chovansky. There was a breakthrough in the 80s. But the bound is huge, huge. The important thing is that he found a bound which is completely independent of the degree. Okay? It depends on the number of monomials and the number of variables. But he only took into account the exponents, so the matrix A of exponents, but not the coefficient matrix. And then there was a conjecture about what could be a multivariate Descartes rule, and it was easily disproven. But the story is that there is no other conjecture in general. There's no statement on what could be a multivariate version of this so simple and useful bound. And then dealing with chemical reaction networks, we realize that in applications, many times you're interested in knowing if you have positive solutions, you have one or more than one. In the domain of, in the realm of biochemical networks, this means if you have multi-stationary, it's an important property. So there was a meeting in Dutch school, it's like over Wolfa for computer science. And we were several groups, and we all had some science in what we were doing. And so we compactified our knowledge into a version of the Descartes rule, which is for at most one solution. That part of it was in a previous work but hidden. And then we only could be able to generalize it to the case of circuits. Circuits means that you have n plus 2 monomials in n variables. Because in this case, if you have n plus 2 monomials in n variables, the codimension is 1. So using Gale duality, that I'm not going to explain, you can land in studying a polynomial in one variable. This is why we could do it. But anyway, the answer is not so easy. So let me be very quick. So I have a system like this. yi's could be 0. No, we have fixed exponents and fixed coefficient, and in fact, the exponents could be real. And the theorem says there is a condition about so we have the matrix of exponents. You put the exponents as columns of a matrix, and you put your coefficients as rows of a matrix. This is the coefficient of the first polynomial, coefficient of the second polynomial, etc. So we fix the exponents, we construct the matrix of exponents, and we have the matrix of coefficients. We have two matrices of the same size. And if it happens that each time, each minor has the same sign, it could be weaker than that. Maybe some of this could be 0, or all the time different sign. Then we cannot have more than one positive root. So this gives a constraint on how many positive roots you can find, the signs of the minors of these matrices. So if you know a little bit about oriented matrices, this means that the no non-zero vector of C is orthogonal, no non-zero covector is orthogonal for covectors of C. This is standard. And in particular, if all the minors have the same signs, which is said they have the same oriented matrix, then this is the hypothesis satisfied. And the subjectivity is, so if Y is a solution, then these are positive numbers. This Y is a positive combination of the columns of the matrix C. So there is an obvious restriction. If I'm able to get the value Y, then Y has to be a positive combination of the columns of the matrix of coefficients. And it happens that this necessary condition in this case is sufficient. So we get one solution if and only if. It can be at most one. We get if and only if this vector is in the positive cone generated by the columns of the matrix. And let me, maybe, I don't know if I want to skip this. Let me move this. But just one thing. So we get, I'm not going to tell you exactly the result for circuits. But the first thing that a mathematician working in algebraic geometry or not in applications start to think of is, what does this, so NA of C is the number of positive solutions of a system with coefficients in matrix C and exponents and the matrix A. One thing, under which things is this number invariant? So the first thing which is invariant, if instead of your equations F1 and F2, you put 3 times F1 plus F2, F1 minus F2, so you multiply the matrix of coefficient to the left by a matrix, the solutions do not change. So it has to depend on the linear span of the matrix in the Plucker coordinate. This is why it depends on the minors, because it depends on the linear span of the lines. It does not depend on the particular equations. And for similar reasons, it has to depend on the minors of C, on A. More than that, it has to depend on the minors of the associated Cayley matrix. It's a matrix is 1, 0, 0, 1, and you put A below, like the one I showed you. So you see that there are the answer has necessarily to be in terms of minors of the Cayley matrix and minors of C. And what we did is that, in fact, we got some sequence, and we got here a sign variation that I'm not going to explain, but it's in terms of this, in terms of what it should be defined. And we somehow related this sign variation to something which is called the mixed subdivision of the Minkowski sum, but let me skip this because we don't have time to tell this. But I would like to stress this consequence. So what's the signature? I have a matrix of size, so my A is, I have n plus 2 vectors in dimension n, and then I put them in a matrix and I add a row of ones because I would like to understand how many affine relations do I have. And then I have a matrix which is n plus 1 times n plus 2. I'm assuming that it's maximal rank, so there is exactly one vector up to constant in the kernel, okay? And the signature is A is the number of positive entries in this vector, and B is the number of negative vectors otherwise. We take the smallest of these numbers. So this is A is the smallest between the number of positive and negative vectors, and B is the other one. So it happens that the number is at most 2A if A is not B, and 2A minus 1 in other case. So what we get from this is that we have at most n plus 1. But we also get if one point is inside the convex hull of the other ones, this means that a multiple of this vector is a positive combination of the other ones. If I put it on the other side, I get just one negative term, and all the other ones are positive. So A is equal to 1. So all positive, only one negative. If A is equal to 1, I cannot have more than 2 roots for any n. In any dimension, if I have n points and 1 point inside, then I cannot have more than 2 positive roots. And the signs of the minors of this matrix tells you the relative positions of the points. So if I can move from here to here, then there will be a 0 minor, and this point goes outside, then all the minors are going to be positive or alternating. So the signs in this linear combination tells you the relative position of the exponents. And this relative position bounds gives you constraints on the number of positive roots. I find this very beautiful. So just to end, we don't know which are the tools that are needed to pose, not even to prove a conjecture, to pose a true conjecture. We don't know which tools are missing. And it's completely open. There is no conjecture, there's no proof, but there is no conjecture of a general result. Thank you very much.